accuracy of the simulation of an impeller. The main objective of the project was to create an impeller to evaluate its character. This original design was made in order to present a higher shear rate than the one obtained from a Rushton impeller.
As mentioned before, the main objective of the project was to create an original impeller design and simulate it, so that depending on its geometry we could obtain a higher shear rate than the one resulting from the Rushton turbine. In order to accomplish this, two programs were used: Autodesk Inventor for the design and StarCCM Plus for the simulations. First, the Rushton impeller was made together with a standard tank with baffles, which are needed in order to prevent vortexing and rotation of the liquid mass as a whole. This type of turbines are known for presenting a higher shear rate. They present a radial flow, and its blades are attached to a horizontal plate for a stabilizing effect. On the other hand, the chosen impeller to make the comparison is a Schauder turbine, composed by a rotor and a stator, has a high degree of radial flow, and is well updated to emulsification and dispersions, which implies that produces a higher shear rate. As well as before, a standard tank was added to the design. In here, we can observe the dimension for the diameter, height, baffles number, baffle height, and baffle thickness obtained for the tank, Rushton turbine, rotor, and finally the stator. At this point, we could start the simulation process, which consists in the volume extrusion, the physical models, the boundary conditions, the meshing, the simulation, and finally analysis of the results. First, the model was uploaded to StarCCM Plus, where the parts were splitted to obtain the stationary part, the tank, the shaft, and the rotating part of the impeller. For the mesh, an automatic one was chosen to apply the general one in all the geometries. That's why it is important to select the rotating and the stationary parts. In here we can see the comparison between the Rushton simulation and the rotor stator simulations. In here we can observe the complete mesh for the impeller design. Thereupon, the fluid rotation and boundary condition as well as the physics models were specified. As fluid conditions, we had a density of 1000 kilograms per meter second, a dynamic viscosity of 0.0001 pascals times second. The rotation conditions were selected for each impeller, depending on its Reynolds number. So there were 6 velocities for each Reynolds and geometry. As boundary condition, there wasn't any inlet or outlet mess, neither air interaction. For the physical models was chosen a 3-dimension implicit on a steady, liquid, constant density, segregated flow, turbulent, and a K-epsilon turbulence. Once the simulations were completed, we can move on to the results. These tables of results was obtained for the Rushton impeller from different types of regimes. In here, it is presented the power, the shear stress, and the power number obtained from the simulations and from the literature, as well as for the sharded impeller. Then, the curve that compares the shear stress with the Reynolds number from both impellers was obtained. In here, it can be seen that although both curves have ascending behavior, the Reynolds numbers, the shear stress for the rotor stator is higher than the Rushton turbine. Then, the comparison between the literature obtained graphical by a given function as simulation data was obtained. The presented results showed that the simulation values are considerably high in relation with the theoretical values until the Reynolds number reaches 100. where the theoretic values and the simulation values have similar values. This implies a high percentage of error for the simulation in the laminar regime. Moving on to the simulations, we can observe the velocity magnitude for the Russian turbine in the turbulent flow. As well as the velocity for the rotor stator in turbulent flow. In contrast, the turbulence kinetic energy profiles from Russian impeller in turbulent flow are shown, as well as the turbulence kinetic energy profiles for the rotor stator in the turbulent flow. Finally, simulations for the y plus value are shown. The y parameter allows us to visualize the definition of the mesh in the part of the boundary layer by considering the effects of the flow near the wall. The values vary up from 0.0062 to nearly 18 from the Russian impeller, and from 0.0083 to 17 from the rotor stator. For the analysis, the following parameters were considered: flow regime, y plus, shear rate, mesh, power number, and errors. In accordance with the objective of the project, the impeller that generates a higher shear rate was chosen, to be comparable with the proposed agitator, the Russian turbine. For that reason, the rotor stator was chosen over all the design and simulated impellers. Taking into account that the mesh was a very important parameter in the simulation and was carefully selected, we chose the y plus parameter to analyze it. The y plus parameter gives information about the quality of the mesh and so the results. For this case in particular, it was possible to observe that for both cases there was an increment when the Reynolds numbers was increasing, due to a turbulent flow that is affected by the presence of walls. The regions that are affected by the viscosity have large gradients in the solution of the variables, and the location of these regions allow us determining successful prediction of wall-bounded faults. However, it is important to mention that the validity of this value lies in the requirements and the nature of the simulation. That is why it is important always to keep this concept in mind to define the accuracy of the results. Now, talking in terms of the behavior of the power number versus the Reynolds number, the Russian turbine gives an approximate value. This means that there is no significant difference between them, because there is influence of subjective in the graphical method, while the numerical solution has a more accurate connotation. For the rotor, there is a representative difference, especially in the laminar regime, possibly by the low rotational speed supply. The torque is not detected with such severity, and in consequence the power is too high compared with the needed. But most important, the models used to describe this phenomena is the simulations, because of all of them were made under the same K-epsilon turbulence model. Also, in addition to all of the aforementioned, for analyzing the results, it was important to take into account that the design of our impeller was used with water, and the Russian turbine generally is used with more viscous fluids. As a result of this, the shear stress is smaller in comparison with high viscosity fluids as oil. Also, power required depends on the resistance offered by the fluid to rotation of the impeller. Now, analyzing the power number for turbines, it is possible to say that is meaningfully higher than for most of impellers, indicating that turbines transmit more power to a fluid than the other designs. Finally, when analyzing the results obtained for the rotor stator impeller, it was possible to mention that gives a better shear stress, which means it is a better option for emulsifications. Also, it gives a higher power number for the same Reynolds number as expected, since it needs more power to print a major shear rate, so energy costs are sacrificed for a greater shear stress. To end up, we can conclude. To sum up, it was possible to obtain a higher shear rate with the rotor-stator impeller in comparison to a Rushton turbine. While the Rushton impeller presented a shear rate of 18.39 pascals in turbulent flow, the one obtained with the rotor-stator for the same regime is 42.35 pascals. The stator rotor has a higher power number for the same Reynolds numbers compared to a Rushton turbine. This indicates that the Rushton turbine requires less power and more energy in comparison to the stator rotor. By taking into account the main objectives of the project, which was to generate a greater cutting